So, now let us look at the travelling salesman problem and see how the genetic algorithm community has addressed this. As we have said earlier, the TSP is one of the favorite problems of computer scientists. And some people call it the holy grail of computer science, but it is not so straightforward to use genetic algorithms to solve TSP, and we have to experiment with different representations, and we have to invent new crossover functions for doing that. So, let us begin with looking at it from a simple perspective first. We can use GAs to solve TSP as follows: create a population of candidate TSP solutions and let the fitness function be the cost of the tour. So, this will be a minimization problem because we want the lowest cost tour to be done. In the path representation, the tour is represented by a permutation of the cities with the assumption that one returns from the last city in the permutation to the first city. So, supposing there are 4 cities, so I write C, A, B, D as a tour. So, it basically says you start with C, go to A, then go to B, then go to D, and then come back to C essentially. So, it is a complete tour. We don't write C again in the path representation because we just look at the permutation of the cities. So, if you remember, our genetic algorithm starts with the selection process where we clone each tour in proportion to fitness. In our case, the cheapest tours are the fittest tours. Then we randomly pair the resulting population and perform crossover, and once in a while we might do a random mutation in the candidate. The first observation to make is that the single point crossover will not work for TSP. So, supposing we have this TSP for these two for these two tours for this number of cities, and we do a random single point crossover, then you can see that the crossover, it has been done at this point, but in the resulting children certain cities are repeated essentially. So, L is repeated, and likewise B is repeated and J is repeated in the first child, and also some are repeated in the second child. So, the single point crossover does not work essentially, the offspring are not valid tours. So, we need something a little bit more interesting. So, we will look at a few crossovers which can be applied to the path representation first, and then we will also look at some alternate representations. So, the first one is called the cycle crossover, and here we have these two parents P1 and P2. The first step is to identify the cycles. You start with O, go to H, then go to H in the first parent and follow its links. So, from H you go to A, so you go to the first A in the first parent, then from A you go to O, and then you have come back to the starting point in the first parent. So, you have identified a first cycle. What does this cycle do? It identifies 3 cities O, A and H which are in the same location in the 2 parents essentially. So, this is the first cycle. Then we start with the second city which is D and do a similar process, go from D to G, G to M to K, and we are now back to D essentially. So, we have identified the second cycle. In this manner we continue till we have identified all cycles in the 2 parents, and you can see that each cycle here is shown by one color essentially. So, the first 2 we had seen and the rest are similar in nature essentially. What we have written here are the cycle numbers in the middle essentially, cycle 1, cycle 2, cycle 3 and so on essentially. Now, we produce the 2 children. The first child C1 gets the odd numbered cycles from P1. So, you can see what are the odd number cycles. We have 1 here. So, these cities, all these are copied into from P1 into C1. whatever I have circled, you can see they have been copied into child 1, and the remaining cities are got from the second child essentially. It gets the even numbered cycles from P2 essentially, which is shown on the top here essentially. So, this is the process. You have identified these different cycles. To create the first child, you take all odd numbered cities or odd numbered cycles from parent 1 and all even numbered cycles from parent 2. So, for example, for cycle 2, parent 2 has G and M, and that has been copied into the first child essentially. You do the opposite for the other child, odd numbered from parent 2 and even numbered from parent 1, and then you get the second child in this fashion. How does this look? So, I have drawn these diagrams which are a kind of a schematic diagrams. These are not geographic locations. So, do not look at the tour as a physical tour. It is just a schematic where I have written all the cities in a circle, and we just want to see how the two tours look after that essentially. So, it does not mean that the shortest tour would have been going around the circle like this, because this is not a geographic diagram, it is a schematic diagram only essentially. So, given these two cities, given these two tours P1 and P2, once we do cycle crossover, we get two different tours, as we can see from here essentially. So, essentially some edges are removed and some edges are added and so on and so forth. The next cycle that we want to look at or the next crossover operation is also a very popular one called partially mapped crossover or PMX. You can get nice illustrations of these on the net if you can go with videos showing how these things are happening. The process of using this partially mapped crossover is as follows, that you identify some cities which are a subtour in each of the two, the corresponding cities, as shown in the shaded areas here. So, in parent 1 we have H, K, M, B, J. In parent 2, in the corresponding locations we have A, D, K, I, C. So, first we do this partial mapping essentially from these cities to the other one tour to the other tour essentially, and then we start constructing the tour. So, we copy the subtour from parent 1 to C1. So, we have copied this H, K, M, B, J, and then we are looking for filling the other cities from their locations in parent 2 essentially. How do we do that? We want to copy the remaining cities from parent 2, but some locations are already occupied. So, for example, the locations for cities A, D, I, C are occupied. So, we can't copy A from parent 2 and I from parent 2 and C from parent 2, because their locations have been occupied by H, K, M, B, J essentially. This is where we start using the partial map essentially to find out where should we put A in child 1, where should we put D in child 1 and I and C in child 1. We do not have to worry about K, because K has already found a place in child 1, because it was present in this subtour of parent 1 essentially. So, K we do not have to worry about, because K already has a place, but for A, D, I and C we want to find locations. So, how do we do that? We start with A. Where should A be in the child 1? C1 is child 1. So, we follow the partial map. We look at where H was and we put A in the location of H essentially. You can see that this location was occupied by A neither in parent 1, but not and nor in parent 2. But this is what partially mapped operator gives us essentially. So, if we have done with A, next we move to D. Where should D be in C1? We do the similar process. We go from D to K, but K is already occupied. Then we go from K to M, M is also already occupied. Then we go to M in P2, and this is where we are going to store D in C1. So, we started by looking for where to put this D. We followed the partial map and figured out that D must go in this location, which is available for D. In this process, we do for cities I and C, and remember that K is already in C1 essentially. So, this is now we are doing I finds its place, then C also we follow the partial map and find its place C. So, now we have taken care of all the tours which are in the all the cities which are in the shaded part of the subtour. The remaining cities are simply copied directly from parent 2 to child 1 essentially, and there is not going to be any conflict. What we are going to get is a legal tour or a valid tour, and this is how the partially mapped crossover operator works essentially. The second child is constructed in a similar fashion, first copying the subtour from parent 2. So, you can see that A, D, K, I, C is copied here, and then the similar process is followed to construct the second child essentially. So, this was the second crossover operator that we have seen for solving the TSP, and this is how the tours look, that the dashed lines represent subtours which have been copied, the dashed and the shaded lines, and the other edges are new edges that have been added to the tour essentially. Then finally, we look at another crossover called the order crossover. So, we first copy a subtour from P to C1 like we did earlier. So, this is a subtour, the same subtour that we had seen earlier, and we have copied it into C1 here, and then the remaining cities which we copy from C2 from P2, we copy them in the same order in which they occur in P2. So, the order is what we have G followed by F followed by O followed by A followed by D. So, you can see that G, F, O, A, D and so on. This is called the order crossover, and this other tour is constructed in a similar fashion. This illustrates how order crossover works. The same subtours which are copied remain in the final tours, but some other cities and their connections have changed eventually. Next, we look at the different representation of the tour. The path representation simply said, for example, this parent, if you think of this as a path representation, you are saying you are starting with city O, going to D, then going to G, then going to L and A and so on. That is a path representation. Now, we are looking for a different representation called the adjacency representation, in which we start off by constructing an index of the cities. So, the index is the alphabetic order of the cities in this example A, B, C, D, E, F, G, and then we construct the adjacency representation as follows, that in adjacency representation the cities are arranged based on where they come from in the tour with respect to the index. So, for example, if you look at the parent tour, you are going from A to H in the path representation. In the adjacency representation, you have stored H here because you are going from A to H. So, every city in the adjacency representation says that you are coming from the index city to that. So, likewise, for example, in the parent you are going from B to J here. So, here we are going from B to J essentially. So, J comes in the second position. So, the city in the first position says I have come here from A, the city in the second position says I have come here from B. Then likewise, you know that this N is here because you come to N from C in the original this thing. So, if you look at this, from C you are going to N, and in that manner we construct the adjacency representation. So, what the adjacency representation tells you is, for any given city you can easily find out where you came from without having to scan the entire tour. You just look at the index and you know that you came from there. So, if you want to look at where did you come from to K from, you know that you came from H, because it is in the location of the index H essentially, and you can verify that from the original tour that from H you went to K. So, this is the adjacency representation. Likewise, you can construct an adjacency representation for the second this thing, and now we are working with these two different representations essentially. So, what are the crossover operators that adjacency representation allows us to do? So, this is the index of the cities, and this is an adjacency representation of a tour. But the problem with this is that every permutation of those cities is not a valid adjacency representation of a tour. And why is that? Because as you can see here, this says that you have come to B from A and you have come to A from B. So, which basically is a cycle within the cities. So, that cannot be a valid tour essentially. So, not every permutation in adjacency representation is a valid tour. So, the question you might ask is, does that mean that the adjacency representation cannot represent the entire candidate space? The answer to that is no, and the reason for that is that in the path representation every rotation of a permutation represents the same tour essentially. So, for example, if I have a tour called let us say B A C D, this is equivalent to writing A C D B. You can rotate it by any amount and it will be the same tour. So, in the path representation every unique tour has multiple representations, whereas that is not the case in adjacency representation. So, I will leave you with a question as to how many representations does a unique tour have in adjacency representation. And the hint is, the answer is not one, but it is not that every tour has many representations. So, I will leave this for you to ponder over, but the point is that there are certain permutations of the cities which are not valid tours in the adjacency representation essentially. You might also recall that this tour is equivalent to writing D C A B. It simply changes the direction. Instead of going from C to D, you are going from D to C, but it still represents the same tour essentially. So, in the path representation some tours will have multiple representations, but in adjacency representation that is different. So, it is not as if we are not covering the entire space. So, what are the crossover operators that we can do with adjacency representation? One is called the alternating edges crossover. So, now remember that we know in the adjacency representation as to from which city you are going to which city without traversing the tour. So, you can construct a child as follows. You start with some city X and choose the next city Y from parent 1. You can do that easily because you just have to go to the index of that city and find what is the city that you are going to from there essentially. Then from going from Y, you choose the next city from parent P2. So, in some sense you are choosing alternate edges from the two tours essentially. If you are starting with city A and if in parent 1 you were going from A to let us say F, then you put that A to F in the child, then you see from where you were or from F where were you going to in parent 2 and copy that tour from parent 2 and so on. So, that is called the alternating edges crossovers. You take one edge from one parent, the other edge from the other parent, and you keep constructing a tour in that fashion. Another variation is called the heuristic crossover.
Sir, one doubt is in alternating edges crossover, we may end up in the same city again, right?
Yes, that's
Also, we may end up in a dead end as well.
Yeah, that there is a problem, and I will just mention that in the sense that you have to be careful that not every way of constructing this will result in a tour. It's a very valid observation. But the other crossover that we can use is called the heuristic crossover, and essentially what this says is that for each city, choose the next city from that parent P1 or P2, whichever is closer. So that is the general idea of we want to construct shorter tours. So you see from which city you are going to a shorter tour essentially. So because of this particular representation, these choices are facilitated by this adjacency representation. But as you pointed out, you have to be careful while constructing children in adjacency representation. So let us say we start with city F essentially. So where is F? This is the city we start with, and we choose the edge from parent 1. So from city F we go to city C, because that is what the representation says essentially. Where should we go from C? That we choose from P2. So from F we have gone to C, then from C you see that this is from P2. So from F we went to C, then from C we go to N, because we are choosing this second edge from P2 essentially. Then from P1, where do you go from N? So N is here, so you go to I essentially, that is the next one. And from P2, where do you go from I? So if you look at this I here, you are coming back to C, but C is already there in the tour essentially. So as you observed rightly, you can form a tour which is not a valid tour. So you have to be careful about that, and the general idea would be to choose the next city somewhat randomly here essentially. So remember that these are devices that we are building so that we can do genetic algorithms, that we want to construct a population of cities and keep churning the population to develop new tours essentially. So the only thing with TSP, as we have seen, is that we have to be very careful that not every permutation of n cities is a valid tour in adjacency representation. So finally, we look at a representation called an ordinal representation, and it works as follows. You start with an index as before. So let us say the path representation is given on the top, and we want to see how we will represent this in an ordinal representation essentially. So we use a numeric index of the remaining cities. Of course, initially all cities are remaining cities. So this is the index that we start with, and now we want to convert our path representation into what is called as ordinal representation. So we will do it city by city. We start with city O, replace the name of the city in the path representation one by its current numeric index essentially. So let us see this example here. We start with O, and we write 15 in the first place in the ordinal representation. Why 15? Because the index of O is 15 essentially. So we are going to represent that here essentially. Then we go to D. Okay, what is the location of D? You can see that D has location 4 in the index. So we copy that 4 there, but what we also do is that we remove D from the current index. So D is no longer in the index, and the index has kind of shifted to the left after that. So this D will go. So E will become the 4th city, and F will become the 5th city, and G will become the 6th city, and so on. The whole thing will shift. That is what happens. We have removed the D from the index, and now E has become 4. So the next city we are interested is in G, and the index of G, as you can see, is 6. So we copy 6 there. and then we remove also G from the index essentially. This process continues, that we just choose the index of the next city and we remove that city from the index as we go along. So, after that, for example, L will become, L was 11 here and it would have become 10 after we had removed that index for G, which I have not shown here, but the process in general continues, and we keep writing the indices of the cities from the remaining index. So, the current numeric index is what is important essentially. Next is A with a index 1, as you can see that is always the case. This will decrement all the other indexes. So, now B will become 1, instead of 2 it will become 1, C will become 2 and E will become 3 and so on and so forth. So, I hope the process is clear, and then we simply keep filling up the rest of the cities with their current index. So, the current numeric index, and the index keeps shrinking as we go along. So, as you can see that the numbers are becoming smaller than we started off with, and this is the ordinal representation of a path tour essentially. So, as you reach towards the end of the tour, you can see that the numbers will become very small. Eventually, of course, it has to end with 1, because by then only one city is left in the index essentially. So, this is the ordinal representation, and you must practice this, and you must figure out how to write a program to convert a path representation into an ordinal representation. What is the advantage of ordinal representation? Why did we do all these complex things? The simple advantage is that a single point crossover produces valid offspring in the ordinal representation. Of course, I have not spoken about how to convert back from ordinal representation to the path representation, and I will leave that as an exercise, and also as an exercise to take 2 candidate tours, convert them into ordinal representation, do the single point crossover and see that you get valid tours actually. So, this whole exercise was simply so that single point crossover could be used here. So, with that we will end with TSP and the genetic algorithm, and move to another nature inspired optimization method, which is to learn from how ants operate.